This recording is going to be about matter, the properties it has, and the changes that it can undergo. Matter is anything that has mass and volume. You need to remember that mass is the amount of matter and volume is the amount of space. Hopefully these are terms that you remember from previous science courses. We're looking at two main types of categories, or two main categories when we talk about types of matter. Pure substances, which are going to be elements and compounds, and they can only be separated through chemical changes, and mixtures, which are just physically combined substances that can physically be separated and they don't have to undergo a chemical change. Physical properties are going to be anything you can describe about it, its color, its shape, its texture, whether it's hard or if it's smooth. Chemical properties, you're only going to be able to see these properties when you're actually changing the matter, such as whether it's flammable, whether it can rust, whether it goes through a reaction with acids. Those things, when we're changing it, those properties are called chemical properties. The types of physical properties we're going to look at are extensive and intensive. Extensive is talking about things that are dependent upon how much of the substance you have, such as mass or volume. Then intensive are things that it doesn't matter how much you have, it's looking at the properties of that type of substance, such as texture or hardness. We know that water here on Earth, we have it in 3 different phases at any time: solid, liquid, and gas. All matter can be in one of these phases. If we look at our diagram and we can see a solid is when the particles are packed tightly together, they have a regular repeating pattern. A liquid is when the molecules or atoms of the substance are spread out a little bit more so they can actually move past each other and they can flow. A gas is when they have so much energy they're able to spread apart from each other and no longer have a definite volume or shape due to the fact they have so much energy they are independent of each other. When we go from solid to a liquid, like if I took an ice cube and I set it on a table, we know it's going to melt. If I leave it there long enough, then it'll go through evaporation. Go in reverse, when you have sweat on the outside of a glass on a hot day, when you take your iced tea outside and all of a sudden water droplets begin forming on the outside of the glass, that's condensation. And then when I take an ice tray and I fill it up with water and I put it in the freezer, I allow it to freeze. Also called solidify, because there are some metals, or the majority of metals are solids already at our room temperature. So when we would think of the word freeze, we have a tendency to relate that with being cold. But for a metal, even if it's 100 degrees outside, it's still going to be a solid. So even though it would temperature-wise feel warm to us, for the solid, that's still a cool enough temperature for it to stay in its regular repeating pattern. So you will sometimes hear freezing, also called solidification. Anything that you change physically, such as if I drop a glass and it breaks, it's changed its shape, it's changed its appearance, but it has not changed what it's made of. So that is a physical change. If I take a piece of paper and I crumble it up and I throw it away, I've changed its shape and its appearance, but it's still the same composition of the substance. Phase changes that we just went through, freezing, melting, condensation, evaporation, those are all going to be physical changes because it's still water. When I took that ice cube and put it on the table, it's just allowed its molecules to spread out and become a liquid. And then they've gained more energy and spread out even further and become a gas. With a chemical change, then we know there's going to be a new form of matter from that. So it's where my ice cube, when it melted, it was still water. If the change, such as if I ran an electric current through the water, then I can completely change the type of matter that I have there. I can split it into the hydrogen and the oxygen gases that have made up the water molecule. There are two main types of mixtures that we're going to look at: heterogeneous and homogeneous mixture. A heterogeneous mixture means when you look at it, you can see the different components that make up that substance. A couple examples that are given here: chocolate chip cookie, or gravel, or soil, or if you have ever had like Italian dressing and you can see the separation with all the little spices that are down at the bottom and then the other liquid, that's heterogeneous because hetero means different and geneous means makeup. So it has a different makeup and it's visible. Homogeneous means it has the same composition throughout the whole thing. So if I made a gallon of Kool-Aid and I poured it into everybody's cup is going to appear to be the same as far as the substance that's in it. Maybe there's a different amount of it, but blue Kool-Aid looks like blue Kool-Aid, whether it's the first, the third, or the fifth glass that I poured. So that's homogeneous. I cannot see what is in that mixture. It looks like one substance, but if I would physically change it, like take my Kool-Aid and put it on the stove and cause it to heat up and begin to boil the water will change to a gas and leave behind the sugar and the Kool-Aid powder that originally was dissolved in it. So it's still a mixture, even though it appears to be only one substance. Homogeneous mixtures, we call these solutions. We talked about Kool-Aid as far as that's a solid, the sugar and the Kool-Aid powder dissolved in a liquid. Some other types of solutions that you can think of um, for different phases are like antifreeze that you use in your car. Those are different liquid solutions that are just simply mixed together. We can also think about our air. We have nitrogen gas, we have oxygen gas, we have argon gas. There's all different types of gas that make up our air. It's not just one. This is a mixture, but yet we cannot see which gas is which. You can also have metal and metal, and these are called alloys. So if you've ever heard of like the aluminum alloy wheels, that's two different metals, aluminum and then a different metal, either zinc or iron or different things that can be mixed in with it that that are then just dissolved in each other, so it's still just a mixture. Brass instruments are a good example, another example for that. Then we can also have a liquid in a gas. If you've ever seen fog, okay, then you know that there you can physically feel the water vapor that's in the air. And or if you've just been somewhere that's real humid that day, you can feel the liquid that's mixed in with the gases. Then looking back at our pure substances, we talked about these are going to be all of our elements and compounds. So our elements, if we have the smallest unit of an element, that's called an atom, and it cannot be broken down any smaller and still retain its properties. So they could also be compounds. These can be broken down into simpler substances, which would be the elements that make up the compound. So compound is simply two or more different elements chemically bonded together. So they can be broken down to things that are simpler, but not physically. It has to be done through a chemical change. The smallest part of a compound. Most of the time you're going to hear it called a molecule. It can also be called a formula unit. That just differentiates between whether it's an organic molecule or an ionic molecule. But for most books and things where you come in contact with it, you're going to hear it referenced as a molecule. All the elements have a chemical symbol. The periodic table of elements, there's over 100, and you'd actually have to get on the website of Harvard or somewhere who's working on the project to see what the largest atom can be made is, to find out how many. I believe right now we're up to 118. But again, we know we have over 100, and their symbols will represent them, and all the symbols are done the same way. They're always printed, and the first letter is always capitalized. If there is a second letter, that second letter will always be lowercase. You will notice that some symbols will seem very different from what the name of the substance is that we have, like iron, but then the symbol is Fe, and that's because we're not using the English form of the word when the symbol was made. They were using a different language. So some of the other ones that you'll notice that are like sodium, but its symbol is Na, or tungsten and its symbol's W. So some of those are just due to different languages why we say one name but the symbol looks so different. One thing about changing any type of matter is it's going to have to take energy. So what is energy? It's simply just the ability to do work, and work causes change. There are all different types or all different forms that energy can can be put into, like light energy or heat. But really it all comes down to just looking at the potential energy and the kinetic energy, because the energy is either being stored or it's in motion and it's being used. So this also lists a few of just the forms that it can be in, like we said, heat, chemical, electrical. We can even talk about radiant energy. Just any energy is still going to come down to whether it's potential or kinetic when we're talking about the chemical reactions and physical reactions that are taking place. As we look at our chemical reactions, we're going to notice that however much energy is at the beginning of the reaction, it is going to also be the same at the end. We're just utilizing it, transferring it, maybe changing it from heat to light, but we're not creating or destroying any type of energy. So a chemical reaction or a chemical change is where a new substance is going to be formed. When you start a reaction, that's what we call the reactants. And then our reactants will yield or produce our products. And that's what you're going to end with. Whatever is made from a chemical reaction or a chemical change has completely different properties than what the reactants originally had. An example would be if you have hydrogen gas and oxygen gas and you combine those, you're going to form water. Well, hydrogen by itself is extremely flammable. Oxygen by itself is extremely flammable. But if you put them together, then we make water, which is what our firemen use to extinguish the majority of fires. So they definitely have new properties from what the reactants were and what our products become. A chemical reaction is not easily reversed. I can take my water and I can put it on the stove in a pan and heat it up, and it's still going to be water. I'm just going to turn it to water vapor. It takes an electrical current, that much energy running through it to get it to separate into the two elements that made it originally. I can tell if a chemical reaction is taking place if I notice that there is a temperature change and I haven't put it on the stove, but all of a sudden it's heating up, or it could also get cool and I haven't put it in a freezer or on ice or anything. So if there's a change in the energy or in the kinetic energy, so I see a temperature change, then that's going to signal a chemical change is taking place. If there's a drastic color change, so if I take a piece of bread and I put it in the toaster and it pops, but it doesn't actually pop out of the toaster and the toaster keeps running, then all of a sudden when I run in there and look, it is a drastic color change. It went from being white bread to being, black because it's been burnt. A production of a gas that can be seen through bubbles. You could also notice a production of a gas because you can smell an odor. That's going to let you know that a gas is being produced. Another indicator that a chemical reaction or a chemical change has taken place is that a precipitant is formed. This is when you have two liquid solutions and a solid comes from it. Whenever there's a chemical change, you're always going to have a new substance formed that will have completely different properties than the reactants, and it won't be easily reversed, the change. Like with energy in our chemical reactions, the mass is also conserved. However much matter you begin with, we end up with the same exact amount of matter. All we've done is rearrange it or recombine them in a different way. So what if it's not just a chemical change where the mass is going to be conserved? Then what about if it is nuclear? Well, or we all know this formula, E equals mc squared from Einstein. E stands for energy, M stands for mass, and C is the speed of light. So it's energy equals mass times the speed of light squared. So what this formula basically tells us is with the speed of light being a constant, you can have a very, very small mass and it still contain an enormous amount of energy. So whenever we go through a chemical change, the total mass and the energy will remain the same.